So our objective today is that we will learn about the Big Bang Theory and the evidence that supports it. Okay? Our essential question is, what evidence do scientists have to support the Big Bang Theory? What evidence do we have that helps us understand that this is a possibility? Okay? Now, the Big Bang Theory is not the only theory out there. It is just the most widely accepted. It is the one that we have evidence for. Okay? According to the Big Bang Theory, the universe is about 14 billion years old. Okay? Now remember, when we're writing notes, we are writing notes to answer the essential question. On this PowerPoint, I have names of a lot of scientists. It's just to discuss those scientists. You do not have to know any of them. Okay? So don't worry about the names. Worry about the concepts. So, this is the theory that we widely accept, and basically we think that it occurred approximately 13.7 billion years ago. So, just think about it as 14 billion years ago. Pretty close. Because truthfully, we're never going to know for exactly. We're never going to know because we weren't there. And as much evidence as we can get, it's never going to give us really an exact date. Okay? So, you just have to know it's about 14 billion years old. Okay? And this is the theory we widely accept because of specific scientists. So, Guy named Friedman and Lemaitre, and I'm guessing that's how you say his name, I don't really know. Okay? Basically are credited for the beginnings of the Big Bang Theory. So these two scientists are the ones that came up with the theory. And they came up with some calculations. So they made a model, and they put in a bunch of numbers, they crunched all the numbers, and they realized that the universe is really not a static universe. Static means that it's not changing. Okay, it's not moving. What they thought, and the calculation showed, is that the universe is expanding. Expanding means that it's getting bigger. So the Big Bang Theory supports the idea that the universe is getting bigger all the time. Okay? So we believe in an expanding universe because of the Big Bang Theory. Albert Einstein, at the beginning, whenever he looked at these things and looked at what the two scientists did and so on, he concluded in 1915 that it wasn't static. He thought that it was getting bigger and bigger. But the astronomers at the time said, no, Albert, you're wrong. There's no way the universe is getting bigger. The universe is the way it is, and that's the way it is regardless. It doesn't matter. That's what they believed. It's hard for people to change their thinking, especially if they believe something forever and ever and ever. It's hard for somebody to say, you know what, I was wrong. I was wrong for 10 years. It's hard. I mean, it's hard. It's probably hard for you to say that you're wrong. And I know, because a lot of times I tell you, stop doing that. I wasn't doing anything. I just saw you. I just saw you. Okay? So it's hard for people to admit that they're wrong. It's hard. Nobody likes to be wrong. Okay? It's not like, yes, I'm wrong. Okay? Nobody likes to be wrong. Scientists really don't like to be wrong because they're intelligent people. Okay? So, astronomers told Albert Einstein, no, there's no way, it has to be static. So in order for them to prove that the universe was not changing, they convinced Albert Einstein. He actually put in a number to his calculations to make it static. Okay? Later on, he realized, I really shouldn't be listening to these people pushing me to say what they want me to say. If my calculations are what it is, that's what it is. It doesn't matter that I don't want to believe in it. That's just what it is. So he actually considered that, and this is just a side note, as one of his worst or biggest mistakes of his career is to actually make up these numbers to try and make things fit. Because the evidence is what the evidence is. Okay? So, thinking about what the Big Bang Theory really is. The Big Bang Theory says that all matter started in one section of space. We're not talking about one little spot. We're just talking an area. So everything was condensed and densely packed into one area. Okay, that's what the Big Bang Theory says. So Big Bang Theory starts off with all matter, all energy condensed into one spot. That's what it means. one spot. Well, think about it. Okay? You have all this matter, all this energy into one spot. Don't you think at one point in time or another it's going to react to each other? Yeah. Right? If I have baking soda and I have vinegar and they're separate, they don't react. If I put them together and mix them in one bowl, are they going to react? Yes. So think about it. I have all this matter, all this energy, one part, it's going to react in one way or another. Okay? So what we believe happened is some type of reaction occurred, and there was a Big Bang. Not necessarily an explosion, but everything reacted, and that energy was sent out and shot out in all directions, filling space. Okay? So because of all that packed in there, something happened. We'll truthfully never know exactly what it is, unless we could recreate the Big Bang. Okay? And everything was shot into all directions, emptying the empty space. Okay? So basically the Big Bang theory is saying that everything started in one part due to something that occurred. Things reacted. There was a Big Bang, an explosion, if you want to think about it that way. And everything just shot out in all different directions. Okay? Filling up the empty space. Now, why do we think this is? So let's get to the evidence, because our essential question is, what is the evidence for this? We can't just say, this is what it is, believe it. Okay? I'm not going to come in and tell you something and not put evidence. So there's reasons for why we believe this. Scientists always look for reasons or the evidence. Well, Edwin Hubble basically tried to support and show what Lemaître said, meaning that the universe was expanding. And he looked at it and he said, well, it looks like the galaxies are moving away by looking at distances and wavelengths. Okay? And he realized that if you look at galaxies, their movement is very similar to a specific point in time. So his evidence were the following. The major evidence is what we call Doppler shifting. I would not write that down. There's an easier way to think about this. Okay? What Doppler shifting is basically looking at waves and how waves act whenever they are coming closer to you or moving away from you. Okay? So, waves act very weird sometimes, and light is a wave. When waves are closer to you, the waves are really packed close together. Okay? When we talk about light and visible light, which gives you all the colors, waves that are really close together are the blue colors. Waves that are really far apart are red colors. Okay? Now, as waves move closer to you and farther away, the wavelength seems to change. The wavelength actually doesn't change. The wave is a wave. But because it's farther away from you, it takes longer for it to get to you, right? So it seems longer. As it gets closer to you, it has less distance, so it seems a shorter distance. Okay? That's where we get what we call Doppler shifting. Now, it's kind of hard to explain it with color just because you don't see redshift and blue shift here on Earth. But we do hear sound. Everybody in this room has heard a siren of one type or another. It be a cop, a ambulance, or a fire truck. You've heard a siren on a car, okay? Nobody hears that, so everybody here knows what that sounds like, correct? Correct. Now, sound also travels in a wave. So light travels in a wave, sound does too. Sound and light, the waves act exactly the same, even though they're two different things. When the waves of sound get close to you, they're really close together. Okay, when the sound gets far away from you, they're farther apart. But here, we don't talk about color. We talk about the pitch. When waves are really close together, it's a high pitch. High pitch. Okay? They're really, really high. That's a high pitch. Waves close together. Okay? When waves are farther apart, they're low pitch. Okay? Low sound, longer wavelength. Okay? So, now think of a siren. You've heard of a siren that's close to you and that's far away from you, right? They don't listen, they don't sound the same. You ever heard of a siren when they're like 2 or 3 blocks away, they sound woo, 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 right? And then when really, really close to you, they're like ee, ee, ee. Correct?
That's true. Like
Now,
in the fire drill.
Oh my
Give me a
god.
second. Alright, so you know that, correct? Now, the ambulance person or the policeman or so on, just because they went by a dime, they're like, oh, let me change the siren. No, siren's the same, right? Siren is a siren. Whatever the sound it's making, that's what it is. But it sounds different to you because when you're far away from it, it is a long wavelength, okay? Because it's taking longer to get to you. When it's close to you, it's a shorter wavelength because it's close to you. Because it's right there, so it has less to travel, right? So, the Doppler effect or Doppler shifting has to do with the wavelength seeming longer or shorter depending on closer to you or farther away. Okay? Does anybody have any questions over the sound?
Miss Hernandez?
Yes?
Do you have Orlando Ortiz?
Yes?
Can you come up to the office? He's going to for a follow-up and coming back.
Okay.
Okay.
Make sure you get the stuff from everybody else. Yes?
Like on the fire drill, like when you hear it in the room, like it doesn't sound like as high, but then like when you go by the button,
It sounds different, right? Yes, perfect. Okay? So basically that's Doppler shifting. That's a Doppler effect. The fact that when you're close to a wave, it's closer together. In sound, it has to do with high pitch. In color, it has to do, in light, it has to do with color. Okay? So,
But how does that make something blow up and make it go everywhere?
that's not what we're
Something
talking
get
about.
it.
We're talking about expanding universe, meaning it's bigger.
All
Alright, so when we talk about wavelengths and visible wavelengths, what we're seeing is we're seeing a shift. When light waves get closer to you, we call it a blue shift. The waves are closer together, they're moving towards you. When light waves are getting farther away from you, we call it a red shift. The waves are longer, they're moving away from you. So, one of the things that scientists have seen and looked at are what we call a red shift. So, they've been studying galaxies and stars, and when they've seen stars and galaxies 10 years ago, okay, they've been tracking them, so they look at them, they look at the way they look, they measure sort of the wavelength that we're receiving from them, okay? And then if they look at those same galaxies today that they did 10 years ago, they look more red. Doesn't mean that the stars are changing color, they're not. But they look more red to us because the waves are now more elongated, looking more red, and that's what they call the red shift. So when they're looking at stars and galaxies, all of them are going through what we call a red shift, meaning they're moving away from us. So if they're moving away from us, doesn't that mean that the universe is getting bigger? It's expanding, right? Because as they start getting farther and farther away, you see more of a red shift. Now, if we would see them more bluish, then we would know that they're coming closer together. So one of the evidence for the Big Bang Theory is a red shift. The fact that when we look at galaxies and stars, they look more red, therefore, they're moving away from us. Okay? Any questions over red shift? So you need to make sure, very important, I would star this on my notes. You need to understand that red shift means that they're moving away from you, that the waves are getting longer. Okay? But at the same time, because the state likes to be tricky, sometimes they've asked about blue shift. Remember, blue shift means getting closer. So blue, if I'm walking towards you, I'm getting closer to you, right? You see blue. If I'm walking away from you, you see red. And there's more distance between you and me, right? Okay. All right, so that's the first evidence. First thing, in order to answer our essential question, which is, what is the evidence of the Big Bang Theory? This is one. Second thing, radiation. Well, if the Big Bang occurred, obviously, there was some type of chemical reaction, right? There is something that occurred that made everything move in all directions. So, Penzias and Wilson, which basically with the Hubble telescope, looked out into space, and they were looking at the farthest ends that they could see. Well, they looked at what they call noise, okay? Basically, waves that are moving, but no longer light waves, just different types of waves. And they figured that at all directions of how far away they see, they saw some radiation. Well, where's this radiation going to come from?
Heat.
Okay, could be heat. Where does radiation come from here on Earth?
Cancer.
Okay, could come from sun.
Oh.
Okay, it causes cancer. Yes, it can cause cancer.
Alright.
I'm sorry. Nuclear products. So basically, if I let a nuclear bomb go in a certain place, isn't that area full of radiation after that bomb goes off? Yes. Okay. So that radiation or that nuclear bomb is occurring because atoms are splitting in half. That's how you get radiation. That's how you get nuclear bombs. So you're allowing a bunch of energy to come off. Well, think about it. If you had everything dense, completely dense in one area, and there's chemical reactions, aren't the atoms probably going to be splitting and making new elements? Because we have, what, 114 now? Some of those are made. But we have a whole bunch of them that are natural, correct? But they couldn't all be there because they've been made over time. So, apparently, whatever atoms were there did chemical reactions. You're going to end up having radiation. And a chemical reaction that big to allow all matter that we know of today to move in all directions obviously had to leave radiation behind. And that's what we see on the outskirts of how as far as we can see is where you see radiation, leftover radiation that we believe is left over from the Big Bang. So that's our second evidence. So our first evidence is redshift. Our second evidence is radiation that's left over from the Big Bang. And our third one is finding helium in the far reaches of Earth. So if we look out as far as we can look, and we look at the different things that are over there, we see that we find a lot of helium in those outskirts of what we can see. Well, think